Herkese merhabalar. Ben Elif Seda Akta, Solar Baba'da iş geliştirme yöneticisi olarak çalışıyorum. Bugün Solar Baba YouTube ve sosyal medya kanallarında eş zamanlı olarak gerçekleştireceğimiz yayınımızda TÜV Rheinland Global Segment Koordinatörü Dr. Christos Monokrosus ile birlikte olacağız. TÜV Rheinland güneş enerjisi sektöründe kalite, güvenlik ve performans odaklı test, belgelendirme ve denetim hizmetleri sunarak projelerin ulusal ve uluslararası standartlara uygunluğunu garanti altına alıyor. Ayrıca fotovoltaik panel ve sistemler konusunda gelişmiş bir uzmanlık yelpazesiyle yatırımcılara ve üreticilere güvenilir çözümler sağlıyor. Bugünkü yayınımız diğer yayınlarımızdan biraz farklı bir yayın olacak. Dr. Christos'un hazırlamış olduğu İngilizce yayını ekranlara getireceğiz. Kendisi ölçüm süreçlerinde maksimum doğruluk konusunu ele aldı. Sizler için bu band kaydına Türkçe altyazı da ekledik. Böylece daha rahat takip edebileceğinizi düşünüyorum. Band kaydı olduğu için de yayın esnasında maalesef soru cevap yapıyor olamayacağız. Ama yayın sonunda TÜV Rheinland ekibinden Pervin Hanım'ın iletişim bilgilerini sizlerle paylaşacağım. Kendisiyle iletişime rahatlıkla geçebileceksiniz. Sorularınızı da oradan rahatlıkla iletebilirsiniz kendisine. Şimdiden herkese iyi yayınlar diliyorum. Ben bu teknik canlı olmayacak olan bant yayınını sizlerle paylaşıyorum.
Okay, welcome everyone to TÜV Rheinland webinar on accurate testing and also band file creation. As Max said, my name is Chris. I'm working for TÜV Rheinland for nearly 15 years now. And today I have this pleasure to talk about accurate testing. It's a very important topic because it is affecting the pricing of PV modules. So the first part of my speech is related to the accuracy testing, mostly focusing on STC, but it's also low irradiance measurement that can also be very relevant. What I have on my outline, first I will give you an introduction. I will explain you what we do. Then I will go into talking a little bit about the measurement uncertainty, the importance of the uncertainty. I will quickly review sources of measurement uncertainty and share some examples with you before summarizing and concluding. And then I will move into the second part. We'll talk about band file creation. So the question which arises is, does the solar simulator measure power output right? There are two things which are important. One is the degree of accuracy of the solar simulator, and the second is the degree of precision. The degree of precision means of how close these measurements that the solar simulator performs are one to the other. But it's also possible to have measurements which are very close one next to the other, like I'm showing you here on the bottom right, but completely miss the target. And the other axis, the y-axis, is the degree of accuracy, which means that the average of all measurements, how close they are to the true value. And it's also possible, to measure relatively accurate, but imprecisely, like we have in the top left box. So the goal is to measure both precisely and accurately. So this is the goal. It's like showing on the top right box. And this will also, when we do that, we perform measurement with decreased uncertainty. And this is why minimizing the uncertainty is very important. So generally speaking, measurement uncertainty is very important. It can increase the confidence for investors and also reduce risk for manufacturers. Broadly speaking, there are three factors which are very important. The first is the reference module creation. The second is the solar simulator qualification. And the last is the evaluation of the measurement practices. And all of these factors will contribute to the measurement uncertainty. So for investors, valid performance data gives end users and investors security and peace of mind in terms of yields and the return of investment. For the manufacturers, precise performance information is crucial in differentiating a PV module manufacturer's product in the market. And now I would like to share an example with you. Let's consider the economic impact due to the measurement uncertainty. So I would say the uncertainty of inline PV module power rating in the industry, in a production, may lie within 3 to 5% if appropriate quality assurance is in place. And if we take into account a power plant which is, let's say, based somewhere in Southern Europe, let's consider a 50 megawatt peak plant. So a difference in measurement uncertainty of 1% can have a monetary effect of more than 40,000 euros per year, assuming a power purchasing agreement of 5 cents per kilowatt hour. Over a lifetime of 25 years, we have like 1 million euros lost. So 1 million euros is a lot of money, and people would understand this. You tell them 1% uncertainty, may not understand it. But generally speaking, the uncertainty is very important and correlates with revenue. And now I would like to get a little bit more technical and review the factors which influence the measurement uncertainty. Generally speaking, we have 3 factors that we measured before. One is related to the reference irradiance, for example, is related to the reference module that they use in production. The second is related to the measurement equipment, the solar simulator, but also the other instruments, for example, temperature sensors and so on. And the last is related to the operator and technique. It's very important not only to have a very good reference module and a very good solar simulator, but also how you utilize these two in the system. So here I have like a list of factors which related to each of these 3 items. We can talk all day, but very quickly, I would say reference of irradiance is related to the calibration uncertainty for the WPVS, which is what, for example, TÜV Rheinland or another test institute which performing the measurement is using to calibrate its own reference irradiance. How the reference module is integrated in a production line, the accuracy in the calibration of temperature sensors, but also the reproducibility of the flasher. Measurement equipment is also very impactful. Here I have on top of the list my favorite, non-uniformity of irradiance, which can have a significant impact of the uncertainty. I will share some examples with you later. The temporal instability of the flasher, how stable the irradiance is during the measurement, the electronic accuracy, but also the accuracy of the temperature sensors, how we connectors that we use, and also, again, the reproducibility of the solar simulator. For the operator technique and the measurement procedure, it's very important that we have a clear measurement procedure, how we perform the IV corrections. People may not know it, but all solar simulators in the world, they actually perform IV corrections on the measured IV. And this is because during the measurement will never be the irradiance exactly 1000 watts per square meters, and the temperature will never be exactly 25 degrees. And then you have to correct for it. So how these corrections are applied can also have an impact. Spectrum mismatch can be very impactful. I will share some data with you later. But also the optical mismatch between the reference module and the test module. Temperature, both the control of the temperature, but also the temperature non-uniformity, and how we use the connectors. And last but not least, it's also, I have seen a lot of users that have all the other factors that I mentioned so far under very well control, but in the end, they forgot to maintain the system. And this may also give rise to significant errors. I will start reviewing some factors. I would like to share some examples with you how each of these factors affect the measurement uncertainty. And I will start with the uncertainty of spectral mismatch. So the spectral mismatch factor is a correction factor for the irradiance, which you apply on the solar simulator, which is using a calibrated reference device. So the effective irradiance of the module will be increased or decreased accordingly to match its output under STC. Generally, you need 4 factors to apply spectral mismatch correction. The first is given by the standard, is the AM 1.5 spectrum. There is no measurement for it. I just copy the standard that is given, the spectrum that is given in the standard. Then we have the spectral irradiance of the solar simulator, the relative spectral response of the reference device, and also the relative spectral response, or if you like better, the relative spectral responsivity of the module under test. Let's go to the next slide. So here I have an example. We are using, the black curve is a solar simulator spectrum, that is class A. We use 2 spectral responsivity curves, the red curve, which is having a different EVA than the blue curve. Actually, the cell technology is exactly the same. You can also see that they have almost the same spectral response throughout. However, because they use a different EVA, they have a different UV response. And someone may say, you know, using exactly the same technology, all the modules match exactly the same, we only have a small difference in the EVA, but actually, because of spectral mismatch and the difference that we have here only in UV, will create a deviation of 1.65%. This is a huge difference for buyers. And how would this affect the IV? So basically here I show you 2 IVs that they have influenced by spectral mismatch. So basically it affects the IAC, and of course the whole IV will shift up and down. It also affects Pmax. VOC is exactly the same, but the main influence is on IAC and Pmax. And a couple of years ago, we did an experiment. We actually used 3 solar simulators, class A+, class A, and class B. And we use a reference and a DUT, a device under test, let's say a reference module and a module that you are going to test, which have different EVAs. So one of them has a UV with cutoff. It falls short on the UV. And the other one has a UV pass. So basically something similar that I have shown you here, the red and the blue curve. And as you can see, regardless of what is the class of the solar simulator, it is very possible to have significant influence from spectral mismatch if you have unmatched reference with DUT. If the DUT and the reference module are matching, you can have small errors even in class B solar simulators. Of course, the class of the solar simulator is also important, but I would say that it plays a secondary influence comparing to having matched reference and matched DUT. So what is the takeaway from this? The takeaway from this is that selection of reference devices is very important. No matter what, it's very important to have a matched reference module with the module in production. This may not always be the case. I have seen a lot of cases in the industry. Actually, the manufacturers very seldom have exactly the same reference module as the module in production. Maybe they have slight changes, but if these changes would affect the optical response of these PV modules, such as class, EVA, or cell technology, then you cannot assume that they have a matched response. I said optical, optoelectrical, actually, also the response of the cell. The cell technology is very important. Okay. And now I'm moving to my favorite thing. I told you before about the non-uniformity of irradiance. So here I'm using an example. I'm using a reference module that we've put on a solar simulator exactly on the same position. But the only difference is that we turn the module 180 degrees. And as you can see, the IEC in one case is underestimated by 0.75%, and the second case is overestimated by 0.55-54%. This would create directly an influence on Pmax. If you see here, because you compare with the true response, the Pmax is very, very little underestimated. But here's the deal. Why it is very important in the industry? Because you say, maybe IEC is overestimated or underestimated a little bit, but Pmax not so much. No, this is not the case. If in production they use IEC to calibrate the solar simulator, here they will say, for example, that IEC is underestimated by 0.74%, so I need to increase the reference irradiance to counter this. And as a result, this underestimation on Pmax, but now it will become an overestimation because you are compensated with additional irradiance, and the irradiance will increase IC. In this case, you will have like an overestimation of Pmax by 0.64%, while in this case, you will do the opposite. You will decrease the irradiance to compensate, and as a result, we will have an error again. It will be close to 0.4%. So the non-uniformity of irradiance is very important. Very often in the industry, in production, actually, they cannot afford to have like AAA solar simulator or AAA plus. They use maybe, so when you have these solar simulators that have a poor non-uniformity, it is very important to use Pmax for the calibration of the flasher and not ISC. Because if you use Pmax, the mistake that you will do on the Pmax will be very small. A couple of years ago, actually last year, we also published a paper in EU PVSec. We studied the effect of different PV module architectures. We use a conventional PV module and a single PV module here as an example. And I'm showing you the differences that we have on the IV characteristics. Conventional PV modules that have the 3 bypass diodes and 3 strings in series, substrings in series, are more affected by non-uniformity. As you can see, the IEC is directly influenced by the non-uniformity, which affects both IEC and Pmax. On single PV modules, we've seen that the underestimation is significantly smaller. However, is still an effect on Pmax. I would also like to say, I would like to move to the effect of temperature on the measurement. Generally speaking, the temperature is affecting IEC by 0.05% per Celsius degree, Pmax by 0.4% per Celsius degree, and VOC by 0.3% per Celsius degree. What I'm showing you here is the IV may look a bit strange. It's actually one IV measures at different temperatures. Keep in mind that I'm showing you half of the IV. So the starting voltage is here close to 24 volts. Okay. And it's also pretty old cell module technology, but it does not matter. It does not matter. What I would like to say is that sensor calibrations issues can affect the uncertainty of temperature. The non-uniformity of temperature is also very important. It has to be measured and considered. We often see in production that modules may not be given sufficient time to adjust to the ambient. They may be measured hot from lamination. And if you refer to the ambient temperature in this case, you may get the module temperature very wrong. So it's important that modules should be given sufficient time to adjust to the thermal equilibrium. There are other mistakes which are mainly related to when you use contact sensors, such as the contact quality and also the thermal capacitance of the contact sensors may influence the measurement. When it goes to infrared sensors that I actually recommend to be used in production, the uncertainty from reflections and the emissivity of the background can also play an influence. Here I'm showing you on the right. This is actually my picture. I'm holding an IR camera in front of the PV module. But because the glass of the PV module is a reflective surface, you are actually capturing the heat emitted from my body on the camera. So what I want to say that if you have heat sources in the immediate environment of the PV module, be very careful how you implement IR sensors. So we recommend that IR sensors are measured at the back of the module because there is no glass, or it's for glass modules, you have to be very careful how you implement IR sensors. You may want to have like a non-reflective sticker put on the module, or you basically need to do an evaluation before you do it. I would say in the end, what I would like you to remember is like, as a figure of merit, you can say that every 1 Celsius degree would affect the measurement uncertainty by 0.4, 0.5%. Then I would like to talk about the connectors. The connectors would affect the series resistance of the module. The series resistance is affecting the slope of the IV curve near VOC, but VOC effect itself is not affected. But if you increase the series resistance, the slope will change, and that will also affect Pmax. What I want you to remember is that PV connectors in the industry are not designed for repetitive mating, repetitive engagements. Typically, they are qualified after 50 engagements. But in reality, in a production line, a connector may engage up to 200,000 times per year. And as a result, the series resistance of the connector of the multiple engagements, matings, may drift. So here we have done an experiment. We use 2 different connectors and we measure the drift of these connectors after repetitive engagement. And generally we've seen that it is possible to have every 20,000 engagement 20 milliohm shift. For a module with IMP close to 12 ampere, an increase of contact resistance by 20 milliohm would yield approximately 3 watts less output power of the PV module. So this is also very easy to fix, but if it's not properly taken care of, it can also drift the measurements. Capacitance. New PV module technologies have a slow response, and they have a high hysteresis when they are measured from ISC to VOC. There is a decrease in power. And opposite, in when measured from VOC to ISC, and it will be decreasing with decreasing voltage. You will have this characteristic here, hump, that you see here on the top of the green curve. The green curve is a steady state response of the module. And the blue one is the one which is affected by direct measurement, and the red one is affected by reverse measurement. So generally speaking, how big these errors can be, depending on the technology. For heterojunction modules, which are hot in the market right now, if they're measured in 10 milliseconds, the overestimation can be like plus minus 10%. So it's like can be like a huge impact. So the technique which is applied to measure these PV modules can be important. In TÜV Rheinland, we use a patented method. We call it dynamic IV, and it's suitable to address a capacitive artifact of PV modules. But I guess this is a topic for another day. We don't have time to go in great detail. However, I would like you to know that PV modules have a slow response, and if measured in a very short time, it's possible to have significant errors. Now, some practical recommendation. So the irradiance distribution in the test area has to be measured, and we need to define optimal positions with lowest non-uniformity for placing PV modules. The spectral irradiance should also be known to us, should be measured, and so we can perform spectral mismatch correction if necessary, or use a matched reference module with the module under test. Modules that have high capacitance, they need to apply appropriate methods to minimize the power losses. And the power verification of production line needs also to be done. And then we also recommend to perform counterflash measurements to verify the accuracy of the measurement. So TÜV Rheinland, we can guarantee that the lowest measurement uncertainty of 1.4% can be achieved, which provides solid confidence in power rating of PV modules to both manufacturers and investors. We offer different services. For the manufacturers, the most relevant one is the reference module creation, which we can achieve 1.4% uncertainty. We can apply spectral mismatch correction, and we can control the temperature very close to 25 degrees. For a mass measurement, we have to, let's say you have to measure like hundreds of PV modules. This is targeting EPCs and investors. And here we can achieve a measurement uncertainty of 1.8 to 2.3%. We don't apply spectral mismatch correction. Usually these people do not have access to the spectral response of the device, and they cannot provide us like a module to measure the spectral response. We can also control the temperature within 2 degrees and overall achieve a measurement uncertainty, which is close to 2%. Right, and with this, I would like to move to the second part of my speech, which is PAN file creation. I will give you introduction and motivation. I will quickly present our test method and protocol, share some experimental results in terms of the performance of different technologies. I will quickly also project to the energy yield and before concluding. So I would like to start and say that the sales price of PV modules is based on the STC measurement. While real operating conditions may strongly differ to the STC. Actually, the STC condition, which is a condition at 1000 watts per square meter and 25 degrees module temperature, it would almost never occur outdoors. If the irradiance is so high, modules would be hot, so maybe close to 40 or 50 degrees. So STC is very practical for a laboratory because you can control it very well in the lab, but actually does not mean almost anything in terms of outdoor performance. And on top of that, I would say that different silicon-based PV modules show different performance characteristics. So all these factors that affect the performance characteristics need to be evaluated. And so the question which arises is how to estimate the energy yield properly, and what is the difference in energy yield between commercial PV modules. There are several factors which affect the energy yield. First of all, it's the temperature behavior, then it's the operating temperature of the PV module. And when I say the temperature behavior, I mean the temperature coefficients. And the operating temperature of the PV module is the temperature that the PV module will operate under certain irradiance. Different technologies may dissipate heat differently, and this has nothing to do with the temperature coefficient of the PV module. Often I see some people being confused between these two. We also have the low irradiance behavior, which also affect the energy yield, the angular response of the PV module, the spectral effects, also the rated power and its stability. And how all these factors blend with the climate, such as, for example, the ambient temperature, the irradiance, the spectral irradiance, the wind and soiling losses would in the end affect the energy yield. So in this work, we have done a evaluation based on PVSYST, which is a software used to perform energy yield simulations. And PVSYST is using PAN files. PAN files contain specifications of PV modules, and they are suitable to compare module data between different programs. We have performed measurements for all the factors that I highlight here with light green. We made a general assumption about the operating temperature of the PV modules and the stability. And we used database information for the climate. We didn't account for spectral effects. The test method that we use for the solar simulator, we use a AAA+ solar simulator. It is traceable to PETABEG, which is a National Institute of Metrology based in Germany. I can provide a reference cell with an uncertainty of close to 0.4%, K2, which means that with 95% confidence. And we can achieve a measurement uncertainty of 2% in the whole irradiance matrix between 100 to 1,100 watts per square meters, and temperature range between 15 and 75 degrees. And here people may say, hey, you just told us before that you can achieve measurement uncertainty of 1.4%. How come you say 2%? This is because before I told you the uncertainty at STC at 1,025 degrees, here we're talking about the whole range of irradiance between 100 and 1,100 and 15 and 75 degrees Celsius. So it is different. And if you go to very low irradiance, maybe you have like a higher non-uniformity. And if you control also the temperature at 15 degrees, maybe the non-uniformity won't be as good as you can achieve at 25 degrees, which gives rise to our uncertainty. For the angular response, we also use a dedicated equipment. We use repetitive buff layers to suppress diffuse light. We use non-reflective black walls to eliminate secondary reflections. We end up with a very specular beam that has like a field of view within 15 degrees. The cone of irradiance is plus minus 15 degrees. And also can achieve non-uniformity within the volume of rotation of better than 2%. And in our test up, at least, we use a small encapsulated sample to perform PV module measurements. We can also do it on a PV module, but also the uncertainty would be a little bit higher. For the spectral response, in our lab in Shanghai, we can perform measurements on an encapsulated sample. In Cologne, we can perform measurements on a whole PV module. Generally, the system that we use is a little bit different, but it's made from the same manufacturer. So we can achieve, we can scan the whole wavelength range between 300 to 1,700 nanometers. We can achieve non-uniformity of class A over the whole wavelength range. We can also have bias light, and we have significant also monochromatic intensity. So saying this, we have like a very high-end system for spectral response as well. So we can practice accurate measurements. The test protocol that we use and recommend for PAN files is we sample 5 PV modules and 1 encapsulated cell for the case of spectral response. These modules are commercial, so we have access to at least 1,000 serial numbers. And we also have access to the datasheet information. We perform initial stabilization to characterize the LID of the PV modules. We perform spectral response to address spectral mismatch losses. And
Merhabalar tekrar. Yayınımız burada son buluyor. Yayın başında da belirttiğim gibi bant yayını sebebiyle soru cevap alamadık bu yayınımızda. Ancak Pervin Hanım'a merak ettiğiniz soruları rahatlıkla iletebilirsiniz. Pervin Hanım da TÜV Rheinland Türkiye Proje Yöneticisi. Burada mail adresini de sizlerle paylaşmak istiyorum. Doktor Christos'a ve TÜV Rheinland Türkiye ekibine de bu teknik eğitimi bizlerle paylaştıkları için çok teşekkür ederiz. Umarım sizler için de verimli geçmiştir. Bir sonraki yayınımızda görüşmek üzere. Hoşça kalın.